So in this talk, I guess I'll give you a bit of a crash course in weather forecasting and talk about how AI is changing the paradigm in weather forecasting that's been around for 75 years and dramatically lowering the barrier to participation. So my background is that before I worked at NVIDIA, I worked at the UK Met Office for 13 years. So I'm a weather and climate modeler by trade, and I'm a atmospheric physicist, an academic originally. And at NVIDIA, we have this program Earth-2, and I'm the developer relationship manager there. And our job at Earth-2 is to help the weather and climate community to apply AI to solve problems. Okay, so we make open source and open science tools, and then we help developers use those tools to solve real world problems. So I guess there's a temptation when you think of weather forecasting to think of the app in your pocket on your phone, right? And that's definitely a big part of weather forecasting. But really, once you start to get into this world, weather and its effect on decisions is pervasive. Here are just some of the industries that we collaborate with in Earth-2 to use these technologies. So, of course, a mainstay of the weather forecasting industry is government agencies who are there to protect life and limb and help with national resilience. It also has a huge impact on the aviation industry, for instance, but also the energy sector is a real sort of a super user of predictions to optimize how they produce renewable energy and to predict demand. A huge effect on logistics. The risk industry and financial services use weather information. And I think one of the things that sometimes can be forgotten, because I guess there's this kind of cliche of the weather forecast being wrong. Weather affects everything, and it's truly predictable. And there are not many things you can say that about that affect your decision in the future, right? But of course, the weather that you've experienced in the past isn't reflective of the weather that you're going to experience in the future. And moreover, it's not even reflective of the weather you can expect to experience today. Okay? So more and more, because the climate is changing, right? And we're experiencing this heat wave now. And more, users of weather data are considering this changing climate as a real practical effect on how they consider weather data. I just wanted to talk a little bit about NVIDIA and how we fit into this whole story. So, NVIDIA, we're obviously famous for our GPUs that have underpinned a lot of the AI stuff that's happened over the last 5 or 10 years. And this is kind of what this looks like, right, these days. This is essentially what we sell as AI factories, the GPUs that go into them, but also loads of the hardware that surrounds that. The reason I make this explicit is that NVIDIA's strategy for a long time has been not just to make the hardware, but to help make the full tech stack to make that hardware useful. So this is where I live. One of these cards over here is me and my guys. And this is really in the image of CUDA that was such a success for us as machine learning and AI really gathered ahead of steam. So simply, I make tools that help people use that hardware for weather and climate. And just to avoid any mystique about this, the business model here is that if we can help the industry get the most out of AI, there'll be more demand for AI hardware. And then at some point, somebody else will buy some hardware off someone else. But Earth-2 has nothing to sell, right? So this is why we're doing this. We're helping to uplift the weather and climate industry. I've got a short video now just to go through some of the different things. It's about 2 minutes that we do at NVIDIA. everybody at home didn't get their hair blown back by the dramatic music too much. But the reason I show this, if you haven't seen this sort of video from NVIDIA before, is this is more than GPUs, right? And really, this was a quick tour through a couple of the verticals that we work with. So there we saw some fluid dynamics simulation using acceleration of GPUs. We saw optimizing telecommunications network, a bunch of digital twins for training robots. And, and there's more. This is just a small subset of a video. We work with biology models and chemistry models. And like I say, the bit I do here is weather and climate. So I suppose one takeaway from this is there's more to AI than large language models. They're a huge component part of what we do, but really we're modeling physics in Earth-2 with AI. Look, I wanted to give you a quick primer on weather forecasting, just so we're all kind of on the same page and how they have worked, and maybe that sets the context for the opportunities that AI is giving weather and climate. So to start a weather forecast, you need to understand the weather that's happening right now. So there's a huge network of sensors all over the world that's run and exchanged between different nations and different companies in real time at high velocity. Because one thing to remember about weather forecasts is there's high velocity information that goes out of date very quickly. So this is happening every second around the world. So we observe the state of the Earth, and those get processed to create a snapshot of the weather right now. These are all disparate observations from satellites to weather stations. My favorite observation that gets used in the industry is elephant seals with hats on with sensors that swim underwater measuring salinity profiles, right? So you can see from that the sheer diversity of information that goes into initializing a weather forecast. And then we use partial differential equations. So it's a big fluid dynamics model on a rotating sphere on a mesh. This is the kind of science that we've known about in theory since the Industrial Revolution. Okay, and this gets solved like a traditional fluid dynamics model. Some things are too small to resolve on the mesh, like clouds, importantly. So we have subgrid scale process, little nested models that heuristically figure those things out. And then you apply it to your problem. But of course, the Earth system is the canonical chaotic system, right? So chaos theory was discovered by Lorentz doing weather forecasting. So you can't just run this once at a weather forecasting center. You might run this 30 times to sample the chaotic uncertainty. And then you maybe do this every hour or two, right? But the kicker here is to do this with fluid dynamics, you need a supercomputer that's of a scale that only major nations have been able to afford in the past. It uses as much electricity as a small city. The models that you use to do this is maybe like 1 million lines of Fortran. It generates every day probably 0.5 petabyte of data, right? And this is happening at high velocity, and you've got to make critical life or death decisions with this data fire hose. So a few years ago, whilst the ChatGPT moment was going on, in the weather world, we were having a similar kind of experience. So this is an illustrative plot. This is the year along the bottom. Up this y-axis is how good a weather forecast is. Now, there's an important caveat here, which there are myriad ways to define when a weather forecast is good or not. This is but one. But this green dashed line is one of the best-in-class traditional fluid dynamics-based weather models from the European Centre for Medium-Range Weather Forecasting. Each dot's a paper with an AI model in. Some of these are NVIDIA papers, and we'll get onto that in a second. And you can see this kind of linear march, and just the same time ChatGPT was happening, these dots crossed the green line, and it started being clear that, I mean, I think it's hard to explain if you're not from this sector, but 5 years ago or more, people just didn't know if this would ever be possible, right? It just wasn't clear that AI was ever going to be able to do this task. But there's no arguing now that these models are at least comparable and in some senses better than the traditional models. So, but what's very important is that you don't need a national scale supercomputer. You can run this on a desktop now. You can run these forecasts on your desk. The inference as well, so even with such a huge supercomputer, it might take an hour to run a traditional weather forecast as opposed to a minute on a GPU with an AI model. And really, when you add all this together, it's dramatically lowering the barrier to participation. So, any of you out there can, I hope, pick up some of the things that NVIDIA and others are making and start finding ways to apply these capabilities to your problems. Yeah, and this is the other thing is sometimes it's tempting to say, well, is it better than traditional modeling or not? I want to be really clear that there's a very important place for traditional modeling alongside AI modeling, but it's simply opening up different ways of doing stuff that wasn't even conceivable before. So we'll go through some of those in a minute. Yeah, so to be really clear, in Earth-2, our job is to build open tools and then help people use those tools. So you'll notice what we don't do, I hope, which is we don't issue weather forecasts at NVIDIA. That's not our job. We work with people who do to enable them. We don't run services or platforms for people to run weather forecasts. We've got Git repos and we've got Hugging Face models. Yeah, okay, so we have a research team who tries to create the best models in the world for various different tasks in weather forecasting. I'll go through some of those in a minute and what they can be used for. And those are open and published on Hugging Face for people to pick up and use and apply. And we try and make them as easy to pick up as possible by providing software to wrap it, which is on GitHub. And we do a lot of stuff that's based on PyTorch. So, you know, leaning into the kind of standard way that people want to consume all this stuff. All right, so I just thought I'd give you a tour through some of the models that we make. So the mainstay of any weather forecasting capability is what you might call medium range weather forecasting. So that's predicting from 2 hours to 2 weeks into the future. And this is our Atlas model, which we published, I think, in February to the world. So we think this is now the best, you know, most skillful is the way we put that in the weather forecasting industry. The best open weather forecasting medium range prediction that you can that's out there. Here it is compared to, these are the observations on the left, the model on the right, just to give you a quick sort of eyeball check. But really the kind of, the level of, you know, resolution and detail is kind of incredible for something that can be run on your desktop. And then I mentioned just now that AI simply lets you do things that weren't possible before. So this is a good example of that. So as I said, to sample from a chaotic system, you run the same forecast multiple times. And this is what you do with traditional models as well. But it's expensive. So rather than 30 times, you can run the same event 10,000 times now to really build out the statistics of the uncertainty around these events. So this is some work we did with AXA to look at the historical record of hurricanes, or tropical cyclones as they're known, and inflate the observational data set because, you know, this probably maybe isn't apparent, but history is only one realization of what could have happened. And this is a way of taking the observational record and multiplying it by many, many eventualities that could have happened but didn't happen to build up those statistics of the risk. We've also done a lot of work with downscaling using diffusion models. So diffusion models have kind of made their name, I guess, in image generation, and you can apply similar techniques to the weather. So if you don't know, the idea with diffusion models is that you take some kind of field, you add noise to it, and then you train an algorithm to iteratively denoise those fields. The idea here is you can start with a low resolution field and ask it to generate that fine scale structure to generate a high resolution field. So here's an example of fields that have been super resolved using CoreDiff, which is one of our diffusion model approaches. This is a model that we released that is trained over the entire continental United States. And at the end, you can see the low resolution field that's the input to this high resolution field. And here's some work we've been doing with the University of Manchester and something that you might think of as adjacent to weather. So this is air quality. This is pollution information. This is actually what I did my PhD on at Manchester, funnily enough. And this inset in the top left is using those diffusion models to super resolve down to city scale. So the coarse resolution is coming from a traditional fluid dynamics-based chemistry model. And then we're using AI to crank the resolution on top of that. Yeah, another new development has been around what in the trade's called nowcasting. So it turns out that traditional models struggle with very short-term, very high-resolution forecasts for reasons we can go into. And so this is a model that is trained straight from satellite and radar observations. I mean, if you were to look at this, and I just don't think you could tell it wasn't true observations, right? So this is emulating the satellite fields at very short-term, high resolution, so 10 minutes, 3 kilometers. So this is the kind of thing that is getting tested at the minute for understanding oncoming storms and extreme events and helping emergency responders. And here's that model compared to some OBS. And I've got a confession, I've forgotten which one's the OBS and which one's the model, and I don't think you can tell. Yeah, same here. Yeah, so I find the emergent properties of these models and these systems fascinating. We don't teach it about storms. These things emerge from the underpinning processes. So yeah, on to what we actually make. So one of the GitHub repos that we have is called Earth-2 Studio. So the idea with Earth-2 Studio is to make it as easy as possible to get set up running some of these models in inference. So it's an open source Git repo, and the idea is to provide a framework which wraps all the different component pieces you need to run a weather forecast. So at its most basic, this is some imports and 4 lines of Python. You need to tell it what model you want to use. You need to tell it what data to start that model from. You need to tell it what kind of data backend you want, and then you add them all together. So just if you can rewind 5 years to where I used to be before the AI AI came to weather forecasting, when you're talking about needing to be a government with a supercomputer and 1 million lines of Fortran. And now we've got to this for something which in many ways is equivalent. So yeah, we have various models available. I think something that's really important to emphasize here is I'm really proud of the models that we make at NVIDIA, and I think we've got some world-beating capabilities to offer to people. But what we're not saying is you have to use NVIDIA's models with Earth-2 Studio. So all these, this list is slightly out of date. There's some more models there now, but all these yellow models are not NVIDIA models that we've wrapped into this library. Okay, so Google GraphCast is there, ECMWF, AIFS is there, Microsoft Aurora, right? So really we're saying here, there's lots of tools for the job, and this framework is generic and extensible, and these are the models that we've offered to get people going. Similar with data sets, here's a smorgasbord of different data sets that you can use to fire these models off. And then just building on the back of the last talk about databases, I don't know if anybody's got any experience with this sort of data, but in some ways it can be quite, exotic. Like it's highly multidimensional and high volume and high velocity. And so some of the data formats that we use maybe are unfamiliar. And so this does a lot of the wrapping of those backends. We work with a lot of chunked, often self-describing formats like NetCDF and also ZAR. There's data models like Xarray, which is essentially a multi-dimensional geospatial aware version of Pandas. But the interfacing with those data formats and data models is built in here, and you can swap between them. And I guess the final comment on Earth-2 Studio is this is we want this to be an extensible framework. So if there's a data set or a model or an IO backend that you guys would like that's not there, we'd love some PRs, that's the way it's kind of designed. Oh yeah, and I think this is really important. We spend a lot of effort doing the kind of unglamorous, boring stuff, which is documentation and training and cookbooks and all this stuff, right? So far from just lobbing a paper out and saying we've got the best model in the world, we really want to make this stuff usable. So here's a whole bunch of cookbooks of how to run different models in inference. We've got a sister GitHub repo to Earth-2 Studio called Physics Nemo. So Physics Nemo is really designed, if Earth-2 Studio is for inference, Physics Nemo is for training and post-training and retraining. And really Physics Nemo at its broadest is about physics-informed AI and how to apply that to various different sectors, including weather. And it helps you in a couple of different ways. I should say it's a wraparound PyTorch, right? So it should look pretty familiar if people are familiar with PyTorch. It helps you pick up a lot of not the trained models, but the model architectures themselves, right? So rather than having to go and back engineer an architecture from some dusty paper and archive, we've done that work to make it easy for you to take off the shelf. It helps with some of the more computer science aspects of of scaling these training runs. So whilst you can run inference on a desktop, some of these training runs can be heavy, and we can help you do that distribution. And finally, there's a lot of stuff around integrating your physical prior understanding of the problem into the way you construct your training, okay, through physics-aware machinery. And if you guys have done PyTorch training runs, this should look fairly familiar. This is for training one of those diffusion downscaling models. So you have a data loader that provides low resolution and high resolution pairs that you define. You set some hyperparameters and some Hydra config. And then you can run it different ways. Here's an example of firing off a Docker container to go and do that training run. And again, documentation, training recipes. So hopefully there's things that you can build off there. That's pretty much it for me. I've left you with some QR codes here. So these are the two Git repos, but on the right, I'd really recommend there's 2 5-minute videos that a colleague has created, which just give you a crash course of Stefan going through and running different code examples and narrating what's going on and how to swap data in and out. So that's a really good way to get a feel for the software. And then down at the bottom, we've got a tech blog where we write up work that we've done with various different collaborations. I should say, actually, something I haven't spoken about as much in this talk is the way we work is we find developers who want to work closely with us on cutting edge problems, and we help them use this and collaborate on the builds with them. So you can see some examples of that in the tech blog with code snippets that you can take away and apply to your problem. So yeah, that's it from me. Thanks for listening.